It's delightful to see you here today for our distinguished speaker. Today we have Sandra González-Bailón. She's an assistant professor at the Annenberg School for Communication at the University of Pennsylvania. She is also affiliated with the Warren Center for Network and Data Sciences, also at Penn. And prior to joining Penn, she was a fellow at the Oxford Internet Institute, so her credentials are strong. So among other things, her research looks at the intersection of network science, data mining, computational tools, and political communication. She and I are co-editing a handbook on network communication featuring chapters by some esteemed members of our own Network Science Institute. And she also has her own book forthcoming called Decoding the Social World. She is also a lovely and delightful presenter, and I'm thrilled to be able to introduce her to all of you today. So take it away.
Thank you, Brooke. Thanks for the kind introduction, and thank you for the invitation to give this talk. It's great to be here, to get to meet those of you I didn't know before, and to get to re-meet those of you that I've known already for quite a long time. And I want to start this talk by telling you a story about why I became interested in networks in the first place. And this story has to do with the puzzle of unintended consequences. That is, with the fact that human action often triggers effects that were not envisioned or intended by the actors involved. And once I have told you that story, I'll go deeper into some of my recent research, which tries to uncover the role that networks play in the emergence of collective behavior, mostly in the context of political mobilization. So I'm going to pay special attention to two papers that are right now under development or under review, because hopefully that's how you can help me figure out ways to take this work further. So one of the first papers that I read as a grad student was this 1936 essay by sociologist Robert Merton. And in this essay, Merton discusses the reasons why it is often so difficult to anticipate the consequences of our actions. He talks about two main reasons why that is the case. One is because of our ignorance, right? Because we only have partial knowledge of the context within which our actions take place. The second is because the world is intrinsically difficult to predict. There is an interplay of forces and circumstances that are so complex that prediction is beyond reach. And this complexity, he argues, is different from mere ignorance, because it is not related to the knowledge that we have at hand, but to the knowledge that we can conceivably obtain about the social world. So reading this article made me start thinking about how to best map and analyze this intrinsic complexity that characterizes the social world. Then, shortly after, I read another one of Merton's papers. This time this one was published in 1948. And this paper was on self-fulfilling prophecies, that is, predictions that cause themselves to be true even when they weren't based on true facts. And essentially what the prophecy states is that if we define a situation as real, it will be real in its consequences. Now, the reason why this article stayed with me is because it imposed a clear limit to what sociologists call social constructivism, which some of you may know borders dangerously the borders of relativism. So if everything is a social construction, there are no absolutes of the possibility of generalizing knowledge, and I don't agree with that. What Merton claims here is that actually for self-fulfilling prophecies to be true, you need to have the right collective resonance, right? You need to trigger a large enough chain reaction for the prophecy to become a social fact, and that is not socially constructed. His classic example involves a bank that goes insolvent because a fabricated rumor of its insolvency spreads, and so everyone starts withdrawing their money, and so the bank becomes insolvent in the end. What this example shows is that just by defining a situation as real, the situation, that's not enough to make it real. You need a collective of people behaving in such a way that makes it real. And so the question that came to mind as I was reading this article was, right, so how do these chain reactions unfold? What activates the positive feedback that allows a self-fulfilling prophecy to become true? And of course, I soon discovered the answer has to do with networks. Brooke kindly mentioned the book briefly, explaining why networks are so important to understand the unintended consequences of social action is one of the goals that motivated me to write the book Decoding the Social World, which is coming out in the fall. And one of the things that I do in this book is discuss how the unpredictability of social life relates to networks and to the unintended effects that derive from interdependent decisions. This unpredictability, of course, also holds the key to understanding social change, which has occupied a prominent place in the history of sociological thinking. I'm a sociologist by training, so I tend to think a lot about how sociologists have been dealing with some of these problems. In the history of social theory, there are many thinkers who have tried to decode the logic of collective behavior and social change, which included the analysis of phenomena like crowd behavior, rumor spreading, opinion formation, social unrest, and social movements. The timeline of ideas can be traced back to Gabriel Tarde, who in the late 1800s already talked about the importance of communication as a channel for influence and contagion. And since then, many sociologists have tried to overcome the lack of robust empirical evidence that made it difficult for these ideas to be tested, but they all encountered in one way or another the limitations of poor measurement. And so, for instance, in the 1950s, sociologists Turner and Killian wrote, quote, "Collective behavior is not yet an area in which generalizations can be presented in precise form and with the backing of experimental or quantitative evidence." Then in the 1960s, sociologist Lang and Lang wrote, "Because of their magnitude and complexity, collective phenomena are not directly amenable to observation under the kind of rigorously controlled conditions most sociologists would choose." And no wonder, right? Like collective behavior is by definition spontaneous and unpredictable, and so this makes it very difficult to analyze. Then in the 1970s, things started to change a little with the first mathematical models that offered the possibility of conducting more sophisticated thought experiments. But again, these developments were limited by the fact that they could not be validated with empirical data. And this is what digital technologies finally changed, right? They made available data sources that we can use to test some of these very old theoretical intuitions. And so the core argument that I defend in the book will be familiar to many of you, and that is that the reason why digital data allow us to solve the puzzle of unintended consequences is because they make networks more salient and easier to analyze. We as social scientists have known for a long time that communication is the force that makes a collection of people more than the sum of individuals. But we can now parse the information that we generate by being social in new, imaginative ways, which in turn is helping us open the black box of unintended effects. And the core chapters of the book look at the problem of interdependence and how to best disentangle its effects from different levels of analysis, which I guess we could summarize as follows. I would say that right now the study of collective behavior follows three main approaches, especially when collective behavior is analyzed through the lens of social media data. The first is the study of aggregated patterns of collective attention with a focus on temporal dynamics. The second refers to the analysis of networks of information flow with a focus on the structural properties of those networks. And the third refers to the individual level mechanisms that make those other higher level dynamics emerge. And what I argue in the book is that by putting these three levels of analysis together, you can start unpacking the question of why human action often results in unintended consequences. Looking back at my own trajectory so far, I started my research on this level of analysis, so networks of information diffusion, mostly as applied to the field of political mobilization. And I'm going to mention very briefly, just to contextualize the rest of my talk, a few of the studies that I've published on this before I start paying more attention to the two other papers that are of interest for this talk, which relate to the other two levels of analysis. So, back in 2011, I published a study with my colleagues Javier Borja and Yamir Moreno, where we looked at the dynamics of protest recruitment through Twitter. And one of the things that we found might not be very surprising to you, but one of the things that we try to measure is how the topology of the network and where every actor is positioned in that network hold the key to understanding information diffusion and the reach of protest messages. A couple of years later, we published a follow-up study where we looked at, with more detail, at the different positions of influence in the network, and we uncovered a group of actors that we classified as getting influential because they only came out as prominent in the exchange of information that was protest-related, There was nothing about their position in the larger Twitter topology that would have helped us identify them. And they built interesting synergies with the actors that we call broadcasters, who were the users that had a broader follower base. Then, more recently, I worked with colleagues from the SMAP lab at NYU, the Social Media and Political Participation Lab, to uncover call-periphery dynamics in protest networks. And so in this case, we analyzed data around the 2013 Turkish protests. And finally, in this paper written with a colleague from Oxford, Ning Wong, we look at the structural holes in protest campaign networks using community detection methods to identify bottlenecks in the diffusion of information. And so I'm mentioning very quickly of these studies to illustrate how I've been thinking about networks as this architecture that is not designed by any one actor, but that affects the consequences of their behavior in ways that are difficult to foresee from their individual positions. So now the papers that I want to discuss, as I already mentioned, refer to these two other levels of analysis where unintended effects also manifest themselves. And I'm going to start with this, with the mechanisms of individual activation that underlie diffusion dynamics and how we can think about modeling those mechanisms. And the paper that I want to discuss is currently under review. You can find it in an archive, and so if you have, I know talks are weird because you can only give so many details. You can read all the details in the paper, and I'll be glad to receive any feedback you may have. This is collaborative work with colleagues in Spain. The leading author is Pablo Piedrahita, who's a PhD student in Zaragoza. And our goal here is to move beyond traditional threshold models in how we think about contagion dynamics. And we do that by thinking about large-scale coordination as a two-step selection process. In the first stage, actors decide if they want to join a movement. In the second stage, they coordinate their actions with those who also opted in, and we pay attention to this second step of the process. Most threshold models refer to the first stage, right? And they focus on the cascading effects of one-off activations. That is, the decision to join a collective action effort. And what prior work suggests is that the distribution of thresholds in these models which accounts for diversity in the motivation to become involved, is one of the key elements in understanding the emergence of large-scale coordination, right? What prior research shows is that the shape of this distribution is one of the key elements that explain the cascading effects of individual decisions to join a collective effort. Another key element, of course, is the structure of the network that connects those actors and how this structure encourages or hinders spreading dynamics. Now, networks, and again, apologies if this is very basic, but networks shape coordination dynamics for different reasons. They shape coordination dynamics by, first of all, creating different centrality distributions, which allow specific individuals to be more or less influential, or by opening more or less structural holes, which constrain opportunities for chain reactions to the extent that they delimit the routes that cascades can follow. And finally, networks also delimit the size and the composition of the groups of reference that surround a given actor, and therefore the number of social signals that each actor receives. Most threshold models assume that activation happens only once, and that once activated, the change of state from inactive to active is permanent, right? And this is the reason why threshold models are particularly adept at capturing the first stage of coordination dynamics. For instance, the decision to join a movement, or in the context of social media, the decision to start using a particular hashtag, and Brooke has done some very interesting work on hashtag activism. So for hashtags to become globally visible, you need a group of people coordinating the decision to use a particular hashtag in a particular point in time. The model we propose here, on the other hand, aims to capture dynamics of activation within adoption. That is, coordination among actors who already opted in, right? So these would be actors who are already willing to participate in a political cause. And the one assumption made by threshold models that we relax in our model is the assumption of single activation. In other words, what we want to do here is to allow our actors to activate repeatedly so that we can analyze how their actions align over time. We have both theoretical and empirical reasons to relax this assumption and allow recurrent activation to be the driving force of coordination dynamics. The empirical reason is that most instances of diffusion do not involve a single activation in time, but many activations building up momentum. And so, for instance, before a protest day, you have several calls announcing the mobilization. These social signals trickle intermittently as a function of the context that actors inhabit, that is, as a function of activity in their networks, in the networks to which they are exposed. And this context is not stationary, right? It keeps on changing, sometimes drastically over time. And these dynamics cannot be kept to just assume that activation is a one-off event. We also have a theoretical reason to relax the assumption of single activation, and that is that the intermittent dripping of information that social networks facilitate often leads to intense spikes of activity. And what underlies these spikes of activity are coordination dynamics that require the adjustment of individual rhythms so that everybody talks about the same issue or uses the same hashtag at the same time. And so again, these dynamics of coordination are overseen if activation is modeled as a permanent change of state. Okay, so our approach follows classic models of synchronized coordination, which we borrowed from applied math and physics. And like threshold models, our model assumes that the motivational structure of actors can be defined by a limit that, when reached, triggers activation. Unlike threshold models, we split the motivation to activate into two components. We have a social component, which depends on what other actors are doing, in this case in the network. And then we have an individual component, which defines the intrinsic propensity to activate regardless of what others are doing. And so what we do is to model this intrinsic component as a function that increases monotonically over time until the upper bound, which acts as the threshold or the activation limit, is reached. The main assumption that we make here is that when actors reach the activation zone, which they do at different speeds, at different rhythms, they will send a signal to the actors surrounding them. And this signal will increase, will make the actors surrounding ego more likely to activate, will push them closer to the activation zone. Now, the speed of activation is a function that contains two parameters. Omega, which determines how quickly the actor reaches the threshold zone, so it defines the concavity of the curve that maps progression towards activation. And then we have epsilon, which is the strength of the signal received from other actors, which in our case is restricted to actors one step removed in the network. And so every time a neighbor activates, they send a pulse that shifts the state of the focal actor closer towards the threshold zone. And so, in other words, what we do with the parameter epsilon is try to capture social influence and the impact that social influence has in individual decisions to activate. Okay, so just to illustrate how this model works, these are the dynamics that emerge in three different network topologies. And so, in the initial state, actors are randomly allocated to different points in their progression towards activation, which means that they pulsate at different times. And this is what the matrices in the first cycles show, right? Like every actor activates at a different time. And just a note, we define a cycle as the time it takes for every actor in a network to activate at least once. And we use this measure as a normalized measure of time that we can then use to compare dynamics across networks. Anyway, as time progresses, the impact of social influence, which remember we capture using via the epsilon parameter, the impact of social influence starts aligning nodes to the same timing, and this is particularly clear in the case of the directed cycle. The undirected version of the cycle, if you look at these matrices here, it requires more time for actors to coordinate their activations. In fact, there's still one actor that activates with its own timing in the last cycle that we show here. And finally, the tree structure is the least conducive to coordination. It's also undirected. And here, the reason why it's the least conducive to coordination is because of the presence of hubs, right? And the greater influence over the peripheral nodes that are only connected through them. These hubs hamper the spontaneous emergence of coordination, and this is why, in the last cycle, most actors still go in their own way. And so, I think that these examples, these toy networks, illustrate quite well the logic of unintended consequences, right? Like our simulated actors behave according to the same mechanisms. What changes are the conditions in which they interact, which in this case we capture through the different networks. And this difference, of which the actors might or may not be aware, like usually when you're tweeting, when you're tweeting, you don't really know how your network looks like beyond the immediate sphere of influence. These differences will lead to very different collective outcomes. And the only way in which you can analyze these differences is by trying to open this black box of how networks mediate collective dynamics. Okay, so the topology on which interactions take place is therefore a crucial element in the dynamics that we want to model. And so we decided to run experiments on 4 network topologies that are sort of more realistic. Each of these networks correspond to a different empirical scenario. And so, for instance, we know that social networks are never formed at random, but the Erdos-Renyi topology could account for a scenario where actors are connected through their online search patterns, right? Say by looking at what others are posting on websites or blogs beyond social media platforms. And in any case, we use this network also as a standard benchmark with which to assess the performance of the other 3 topologies. The regular network offers a way of mapping interdependence when it is highly structured by logical or space constraints. So for instance, during the 2014 umbrella revolution in Hong Kong, social media and other internet-based modes of communication were censored by the Chinese government. So protesters had to use alternative ways of communicating, like Bluetooth technologies. They use Bluetooth technologies in their cell phones to create mesh networks and coordinate their actions while on the streets. These networks do not rely on online servers and are therefore more difficult to monitor by third parties. It's not impossible, but it's more difficult. But they require physical proximity. They are only feasible when there is a large number of people concentrated in restricted spaces, like concert halls, stadiums, or in this case, a few streets within the same city district. And we use regular networks as an approximation to that sort of scenario. And then, you know better than I do that there's a lot of evidence suggesting that many social networks exhibit the small world and scale-free properties, especially online. And so that's essentially the reason why we decided to use those topologies to run some experiments on them. Just so that you can get a sense of how this whole thing works, this figure here shows what happens with the levels of coordination as the system evolves with a fixed epsilon on a small world graph. And so the curves here track the fraction of actors that activate simultaneously. And as expected, high omega values, which in this example is the same for all actors, lead to faster coordination, right? As omega decreases, the time to full coordination increases. And at low values of omega, system-level coordination is unattainable. This is a condition under which only small clusters of coordinated nodes emerge. So, some results already. So this figure here shows the results of expanding the analysis to the wider range of parametric combinations and to the 4 network topologies. Every dot in these heat maps corresponds to a combination of epsilon and omega. The color scheme indicates the time that it takes for each combination to reach large-scale coordination, which we define as having at least 75% of the nodes activating simultaneously. For each point, time is averaged over 100 realizations of the simulation. And essentially in this scheme, lighter colors indicate earlier coordination. As the colors get darker, coordination takes longer to emerge, and black signals that coordination wasn't possible. And essentially what these results suggest is that all networks are capable of generating coordination in scenarios with strong to moderate social influence. As long as you have a strong to moderate epsilon, large-scale coordination will ultimately emerge, regardless of the propensity to activate of the actors, regardless of the omega value, and regardless of the topology. However, as epsilon starts getting smaller, which means that the strength of social influence diminishes, actors need to have steeper inclinations to reach the tipping point for coordination to emerge. And after some critical point, there's no amount of actor predisposition that can overcome the lack of substantive social influence, right? These critical point changes across networks, scale-free networks turn out to be more stringent, and that is because of the effects that hubs have in the activation of other nodes, as I illustrated before with the tree structure in the toy network. Now, of course, it is a big simplification to assume that all actors have the same propensity to reach that activation zone, and so in the second set of simulations, we introduce heterogeneity in the distribution of the omega parameter, as illustrated here. And so now the vertical axis in the heat maps measures the standard deviation around the mean in the distribution of omega. What the results of this second set of experiments reveal is that heterogeneity in general is bad across all networks, right? And this supports the intuition that for a cause to grow large, actors need to share predispositions, right? Like if you're going to coordinate a large protest or a large mobilization, you better try to do that with people who are also inclined to work hard for that to happen. And once again, the scale-free network is the most restrictive structure, but as long as ties channel some social influence, coordination arises fast. Although then there's a very abrupt transition to no coordination. All right, so what do we draw from this? What are the main conclusions that we derive from these findings? Well, first of all, the first conclusion is that compared to other network topologies, centralized structures perform significantly worse at facilitating coordination, all else equal. And I'm not going to bore you with details, but this essentially contradicts some of the findings of prior models that some sociologists did on critical mass. Centralization is bad, according to our findings, which is not what those prior models found. Second, we also find that there is a critical epsilon for all topologies. That is, for a given network and omega, there is always a value for the social influence parameter below which actors will not achieve coordination. And this critical value changes across topologies and is particularly stringent for scale-free networks. And the third conclusion that we draw from this is that the timing of activations and most importantly, the temporal correlations that arise from that are an important element of coordination dynamics, right? And we cannot capture those dynamics with threshold models. And so obviously there are many extensions that we could incorporate to the model to make it more attuned to how real networks operate. And maybe you have some other ideas. And so one extension that we already thought about was to add heterogeneity in the distribution of epsilon. And so if epsilon is the parameter that we use to capture social influence, it makes sense to allow the strength of the ties to vary, right? Like, so the one thing sociologists know is that not all ties are equal. But of course, this would imply deciding how we distribute epsilon, right? Like, it's just a random distribution wouldn't do either, right? Like, so ties within clusters are stronger than ties bridging structural holes. And then the other related extension would be to make the distribution of omega conditional on network topology, and in particular to clustering, right? Like, again, like birds of a feather flock together. So people who are very highly connected and with high transitive levels, then they are likely to share more similar omegas. And right now, we just distribute those parameters randomly in the network. And there's a bunch of other things that we could do, but we haven't done them yet. We might do them in the future. All right, any questions about this? Dave?
I don't know, a question or observation point. I'm thinking about this, and I'm also thinking about, we're discussing actually in the social networks class, briefly Patrick and Amsel's Medici work, where basically they argue that the Medici were able to mobilize more effectively because they're in the center of the network, whereas the anti-Medici they mobilized a lot but not coordinated. And he has a nice excerpt in the paper about the crowds, the anti-Medici sort of mobilizing at different times and not able to get their act together. And so I wondered to what extent that you find what you find, because you really look, I believe, and correct me if I'm wrong, you're really looking at activation or non-activation, so like ones and zeros. But if we think that there may be a need, like, you know, there may be a need to show up at the same place at the same time, and that if you have polycentric distributed leadership, that you may all show up for March for Science in different days or something like that. The biologist this day, the network scientist that day, or whatever. That would be problematic, and whether there's a modeling choice here that around activation, non-activation, that drives the findings about network topology, and if you had a different model for like convergence on the same value, showing up at the same place at the same time, that, for example, more centralized network, just as an example, might be much more effective.
Yeah, so the process that we had in mind is essentially communication in social networks, right? So how come the people, like when a new hashtag is created, how does that diffuse in the network in a way that a lot of people start using the hashtag to make it? How many hashtags disappear without no one noticing them, right? And some of these hashtags really become sort of banners of political movements, for instance. And so those are one of the dynamics that we had in mind. And really the only thing so it's a very simple model, meaning that activation can mean a number of things. But mostly we were thinking about sending signals in the form of messages, right? So those could be either sort of circulating mobilization campaigns, so that a lot of so that you increase the number of people who are aware of that and might start disseminating that information as well. And the strength is in the numbers, so the more people that start disseminating piece of information around the same time, that's when things become trending topics, for instance, on Twitter, right? That makes a difference. The timing of your messages impacts visibility. That excludes a bunch of processes. I wouldn't say that they're very cheap.
But even something like hashtags, social convergence around certain conventions is really important. So like if you had, and I'm sure there were a lot of hashtags that would say Black Lives Matter, and I'd be interested in Brooke's take on this, but I'm guessing that there were certain central hashtags, and that it was actually pretty important that there be some hashtags that were like the convention to enable a system-wide discussion. And so it's not just hashtags or not, but it's like there are, and indeed actually I had a paper on this years ago looking at the emergence of hashtags after the debate, and the competition of like this was after, it seems so sort of sweet back in 2012, the kinds of things like like Big Bird, like the Big Bird hashtags, right? There are like a whole bunch of Big Bird hashtags after on the debates, because Mitt Romney's like utilizing Big Bird, but in any case. But there were like a bunch of them, but then they competed and some actually won and others died off, right? And so, and so there's an interesting question of diversity versus homogeneity in that hashtag ecology for social movements.
So I guess what you're saying is a third extension, right? Which instead of all the signals being equivalent, so there will be competing signals. And so it wouldn't only be a matter of understanding coordination, but also which signals manage to attract a large number of people using it, and so they end up sort of conquering the network and eliminating. So that would be we can't say anything meaningful about that because we don't have competing signals, right? But it would be a possible extension. Yes.
I don't want to go down this path too
slowly.
I'm trying to get to the end. But sort of a version of that would be nice just from the data you've already got would just be to fix omega and epsilon or whatever and run the network until it reaches whatever its asymptotic state is. And then give us like the plot over time of like the size of each of the coordinated communities, as it were. So you can imagine the densely connected ones, the plot would just look like everybody flashes on, everybody flashes off. But I would imagine that the scale 3 one would have sort of this nice kind of tail of like different communities of different sizes, each of which are out of sync with each other, but you can still give us sort of what the plot looks like to show us whether it's just a bunch of disconnected nodes in a long tail that are all kind of flashing out of sync, or whether it's different sizes at different scales. That'd be kind of interesting just to see.
Yeah, so the idea here is that how does the large-scale coordination emerge? Is it just like you have an epicenter and it starts like sort of ripping out? Or do you have different clusters that at some point merge together, different clusters with different timings that at some point start converging together? So suddenly you have these two huge classes of synchronous nodes that
Or maybe it never converges. Maybe you just have a bunch of different size things all are out of sync with each other, but coordinated within each other.
We do know, but so we don't have all the data necessary to test what you're saying, and the reason is because these simulations take forever to run, and we couldn't keep all the information. I mean, it's at 10,000, so we only kept the size. We only kept, as far as I can remember, we only have the size of the nodes that, after every cycle ends, we count how many nodes activated simultaneously, and we retain that. We don't know anything about their position in the topology. We don't know how far away they are in terms of half length between them or something. So retaining that information would make things even take longer. But it's so essentially we would need to run the simulations again. We don't have the data, but why not? Like, we would do it, right? And I think that would shed additional light into how topologies mediate these dynamics. So good point. Thank you. There was a lot of questions. Yeah, go ahead.
Have you thought about, or are you accounting for the bidirectional influence of online and offline communication, especially in things like the umbrella revolution, where you might have one person who has the mesh networking app that's talking to a bunch of people in person, but is coordinating in a broader sense?
I don't. I wish. No, I haven't. Like the online offline kind of link. It's my $1 million. I wish. And also in the context of the Chinese umbrella, the Hong Kong umbrella revolution, I would hesitate to even know who these people are. Like it's high risk. And so I don't have any data about I don't think anyone has data on these mesh networks that emerged, other than there were that was so anecdotally we know that people were communicating Bluetooth to Bluetooth, and that's how the message is diffused on the streets. I doubt anyone has that data. It's difficult to obtain, right? Like, it's not stored in any server, and even so, and I would be very hesitant to collect it because the reason why protesters use Bluetooth technology was so that they could go under the radar, right? And so the way I think about that problem is, okay, let's build a simulation that sort of replicates stylized facts about those mesh networks, but it's not based on real data. That could potentially lead to identifying these people. That would make me very uneasy.
So you would not take an approach where you would just model the actors and simulate it? Use real data
for that particular, so I gave that example, right? Like, so you can also think of a stadium. I mean, I would gladly collect data on how people in a football stadium, like, say that you also, like, in emergency situations sometimes, when infrastructures collapse, mesh networks come out as an alternative way of communicating. And then in that context, I wouldn't have any problems of collecting the data if I could. I don't know how you would go about it, though. But not in the context of the Hong Kong protest. Yeah.
So I was wondering, you did count the fact that different actors can have different levels of influence. But what if that heterogeneity is correlated with the degree of the actor?
With what? With the?
Well, what if that heterogeneity and their ability to influence is correlated with their popularity? What if the central nodes really do make me more likely to come out than if some random node who I happen to be friends with is?
Yeah, good point. What if? I'm sure it is, empirically speaking. And that's why, these would entail thinking about how we add heterogeneity to both the social influence parameter and the omega, the intrinsic inclination, so that they are correlated with topology. And then that would be one possibility, right? Like your centrality in the network. So nodes that are central in the network tend to have a higher omega, or their ties are more important. The epsilon of the ties is higher. And then you could test different possibilities as to how prestige, say, mediate these dynamics. And this is something we haven't done, but we could that I think it's important to do. And maybe you can do it, maybe.
Yeah.
But yeah, a good point. Yeah. All right, another question here.
I'm trying to figure out which question to ask. I like this talk a lot, in part because it's very, the words you're using to describe this is very neuroscientific too, where you can imagine this as like a brain trying to coordinate a lot of signals, and eventually one of them wins out and does some action, basically.
Because the brain is a complex system too, right?
It is. So, in terms of when you're trying to model actually this activity in the brain, you never know what the latent underlying node level parameters are, or their thresholds for firing or not firing.
Yeah.
But you can kind of get closer and closer to that when you get more and more data. And so when you're trying to model like an actual population based on something like this? Are you trying to infer the nodes in the real world as parameters, and if so, how?
So yeah, so again, one of the questions that I kept on asking myself when reading all these threshold models, and Randall-Vedder's threshold model is my favorite. I mean, that paper is one of my favorite papers also. But the question is, how do you infer the threshold distribution, right? And so how do you empirically determine what that distribution looks like, right? And so you could think about asking people, so how likely are you to go and protest on a given day? Or you can use observational signals in the sense that people who tweet more about politics, you can infer that they will be more likely to activate, and so their thresholds will be higher. But it's not that we have clear, sort of a clear anchoring to these thresholds, and in the case of our model, the omega measures, we have more information about the strength of ties, but again, like the range of possible metrics is why. But the starting point here for this modeling, the motivation was we know that decentralized networks are used over and over to allow people to coordinate on a large scale without central organization, much in the same way that your brain operates without a command. And so the question is, can we, and we don't know under what conditions these things happen. We don't know what the thresholds are, we don't know. So that's why we experiment with this range of values, which are stylized representations of way more complex. And so on the basis of what we try to do, in fact, is say, okay, so we know that people coordinate online often. We know that most online networks are very skewed in the degree distribution. Some of them are scale-free, and we know that these are the most restrictive structures according to our results. So what we deduct from this is, well, then online networks must channel sufficient social influence to allow coordination to emerge. Otherwise, according to our assumptions and our models, it would never happen. Otherwise, it wouldn't happen, right? Like, so for coordination to emerge, you need some moderate to strong social influence. You need social influence to be channeled through the ties, otherwise it would never happen. And so that's why we kind of restrict, of all the parametric combinations we consider, we are likely to be in this region, right? because we know that coordination happens.
Mm-hmm.
But it's a simulation play, it's not based on anything.
That's cool.
How are we doing? Oh, yeah.
You just answered my question. My question was, do you validate the models using any real-world data? You just said your last line.
No, but some of my colleagues, so Pablo has another paper where there's Pablo Piedrahita, the leading author in this paper, he has another paper where he looks at cascade sizes in social media, the size of cascades, and that's kind of the size of the coordination. So, the size of a cascade would be equivalent to what we consider here coordination, and the model replicates the distribution of those sizes.
So that's on
on the
Twitter
aggregate.
data?
What's that?
That's on Twitter data?
Yeah, it's Twitter data. Yeah.
Maybe something I didn't understand. So the model clearly explains how coordination emerges, but how does it die down?
Yeah, good point. So the model is not designed to think about that, but obviously, Black Lives Matter is still kind of, in a few years, maybe no one remembers that hashtag anymore. So that's another extension, right? So we only consider the emergence of coordination, but not how that might start disassembling again. How would you start thinking about that? What would you add to the model?
So when you talk about the repeated activations,
Yeah.
I was thinking of like having some sort of a threshold or like a time scale for
So
maybe even the activation of the network could influence it, or like the competition with other ideas could affect this rate. But basically, there should be some continuation over time.
Yeah. Yeah, it could either be fatigue at the node level, so these nodes at some point stop reactivating with some decaying function.
Yeah.
Or we have these competing signals, and we have constant, if we feed in the model with constantly new signals, then something takes over, and all prominent hashtags stops being prominent because something more powerful comes out. Yeah.
Well, I say to that point, it's important to distinguish between a system that's coordinated becoming uncoordinated, a fragmentation, versus simply cessation. I think cessation is what you see more likely in these protest movements, where just they move on to a new cause, or the event happened, or a new event. I think it'd be an entirely different story, and probably really interesting to see in what rare cases are they coordinated and then they somehow get out of sync.
Yeah, getting out of sync, yeah. I have to think more about that now. But I think it would entail a different model with a different, it's a different paper.
Sorry, one quick follow-up.
Sure.
So, in the digital world, one human can correspond to more than one node.
Yeah.
Unlike the real world. So is there a way to account for that in the model, where can you see when there's one human corresponding to more than one node, even like in totally separate networks even?
Yeah. On this level of abstraction, the model is agnostic. Our nodes can be individual actors or collective actors. They can be, I don't know, news organizations sending signals. It doesn't really matter on the level of abstraction that we are, on which this model operates. Why would you think it, empirically, why do you think it matters? Because, so the one reason I'm just right now thinking it would matter for is, so if you have, is because the strength of the times for some actors, again, like if you're the New York Times and you send a signal, then that would be more influential on other people than, say, retweeting, than if you're someone that no one knows.
Well, I'm thinking more about people who might have multiple accounts, or even using things like bots and whatnot to simulate.
Well, bots, but that's an interesting question, right? Because bots are trying to coordinate, like bots are trying to mediate in this dynamic so that they can coordinate things in a particular, sort of to take them in a particular direction. And it would be so. So they would behave differently, right? Bots behave differently from humans in the sense that the rates of their signals, so the timing of the signals is sort of, it's different, right? And so that could be incorporated in the model, yeah.
But if I'm a human and I could have 5 accounts on Twitter, all posting and retweeting each other, but then even having separate follower networks.
I don't think that matters for the model. But it matters in the sense, I like the bot suggestion, right? Like, so bots are definitely not following the same tempo as the average human. Like, humans sleep and then they disconnect, and bots are programmed to bombard the network with messages. So again, what you're suggesting is another extension where we have 2 types of nodes, and every type is driven by different mechanisms, essentially. And so it would be interesting, yeah, so I think it would be interesting to experiment with different assumptions on how bots can distort these dynamics intentionally. Yeah. How am I doing with time? Should I just cut? Because I haven't had a paper to talk about, but I don't think I have the time. So I'm happy
It's
to.
10:53, so the next group you're meeting with is at 11,
So no. So no. So if there are other questions.
Short, is it a short paper?
3-minute summary.
Not really, but
I have a question about the pragmatics. So the implications in a pragmatic sense, so if I'm an activist or an activist organization, seem to be to try to increase the density of my networks, right? So if we move from scale 3 to a more small world topology, we have more opportunities for coordination.
yeah. Yeah.
Is that, first of all, does that seem right to you?
Yes. So structural holes are bad for coordination.
Okay.
Structural holes where you have, and then that leads you to having hubs that are the only ones spanning those.
Okay. And then building on the bot comment, could that potentially be a strategy? I'm all jazzed up lately about activist bots. So could that, bots can also behave in sort of non-human linking ways, right? So you can create, human beings like have this tendency to create hubs in the quality, right? So we have these social tendencies in the way we create our network ties, particularly in social media. So bots can subvert that, right? So bots can intentionally try to create diverse links. They can try to create links with people who are relatively inconsequential.
Yeah, you can engineer bots for the public good.
Right.
The thing that we don't consider here that these networks change also over time as a function of the information diffusion dynamics that take place in them, right? And so some bots try to embed themselves in networks so that they seem more real and so that their impact is larger. But people decide to create or not ties or remove ties as a function also of how, the information that the different accounts publish and whatever. And so again, I'm trying to answer your question in the sense that what would be the implications of this work? Well, I mean, yes, I think you're right that density is good. On the other hand, these networks never remain stable. And I know there's a few papers where they consider how, say, information cascades lead to more time formations because you suddenly become aware of some account, and then you decide to follow that person, and then they follow you back. And so it's not that the topologies remain constant in our experiments, and then we only look at coordination dynamics, but the coordination dynamics that we're monitoring will have internal impact on the topology of the network. And so the two things are co-evolving at the same time. And so thinking about implications is kind of a tough, you might change your network because you want to build a topology that is more conducive to coordination, but other people will be changing their networks as well, and so you have control over that, right? And so that's another thing we don't consider here, how topology and the diffusion of information dynamics affect each other. And they do. I think it's enough evidence we know that they do.
Some experiments to see if we can
So many
change the way.
experiments, yeah.
Change the way.
All right, so I think I'm done.
Okay.